Next on the integration techniques list is trigonometric substitution, my favorite one of all. I don't know why this is my favorite one. Maybe because I enjoy trigonometry. Maybe it's because these ones really work out so beautifully when it comes to doing the substitution. But either way, this is a good one. So, trig substitution. First off, there are three roots that we're going to look at. In these roots, a is a constant and u is a function of x. These roots should look somewhat familiar to you. We've seen some of them when we did inverse trigonometric functions. And these are also going to show up in trigonometric substitution. And if I'm going to be honest with you, the root isn't even the important part, because the root doesn't even need to actually be part of the problem for us to do the substitution. It's the pieces inside the root. So again, remember, a is a constant and u is a function of x. Okay? And so an example would be, say, the square root of 9 minus x squared. That would fall into the category of this root. And again, the root's not really the important part. It's the 9 minus x squared. It's the constant minus the function of x squared. So there's going to be three identities we need. Those three identities are nothing new. It's the Pythagorean identities. It's two identities ultimately. So there's the Pythagorean identity for sine and cosine. In this case, I solved for the cosine squared. Then there's the secant tangent one. We're going to look at it two ways. One is that secant squared equals 1 plus tan squared, or that tan squared equals secant squared minus 1. Okay. So there's a particular substitution that goes along with each root. So if we have the square root of a squared minus u squared, there's a particular substitution we're going to go through, and I'll go each one individually. And there's also a geometric picture for a right triangle that uses all the same pieces as well. And then there's the square root of a squared minus u squared substitution, and then the square root of u squared minus a squared substitution. So we'll look at each one individually. We'll do an example of each one, and then we'll do a couple more examples. First one is the square root of a squared minus u squared. So what this says is that if we were to let u equal a sine theta, and the square root of a squared minus u squared would then become a cosine theta, we could then switch our integral from an integral of, say, x or even u into an integral of theta. It's a substitution, right? We've done substitution already. We've done substitutions where x turns into u's. In this case, we're going to let x's turn into thetas, essentially. And our new variable is going to be theta. And what we're going to do is we're going to take algebraic expressions out of the integral. This is an algebraic expression. And we're going to replace it with a trigonometric expression. Now, how does that work? We'll have to show you. Why does it work that if we let u equal a sine theta, that the square root of a squared minus u squared equals a cosine theta? I'll show you two reasons why it works. But nonetheless, what we're doing is a substitution that will take, again, algebraic pieces, specifically say like this square root, out of an integral and replace it with a trigonometric function. Which lots of times you'd think, well, why would I do that? Typically we use substitution to make integration easier. Switching to trigonometric functions may not necessarily seem that it would make integration easier, but it does. Okay, so let's look at this. Let's say I have the square root of a squared minus u squared. in that square root, if I were to let u equal a sine theta, I was to make that substitution, so a sine theta would get plugged in here. Look at what happens. I get the square root of a squared minus a sine theta squared, which would then give me the square root of a squared minus a squared sine squared theta, because I square both of these. These both have an a squared in them, so if I factor that out, I have an a squared times 1 minus sine squared. This is the Pythagorean identity that we were talking about, so that would be equal to cosine squared. Now, these are multiplied together, where both being squared, and I'm taking the square root of it, so that'll all cancel, giving me a cosine theta. So you see, that's how this square root turns into this, but only if we use this substitution for u. If I use a different substitution for u, this doesn't simplify as nicely. So that's one reason why it works. Now, you don't have to go through this whole thing every single time. You need to remember that for this square root here, this is the substitution that will turn the square root into a cosine theta. That's the key to this. The key to this is memorizing this right here. Okay. Now, there's another way we can see that this works out, and it's by looking at the triangle here. So, if we said u equals a sine theta, that's the substitution we want to do. That's the same thing as if I divide by a, saying that the sine of theta equals u over a. Now, if I were to draw a right triangle with theta as this angle, it says if I take the sine of that angle, I should get u over a, which tells me that the opposite side of this triangle should be u, and the hypotenuse should be a. Now, if I did Pythagorean Theorem, such that this side squared plus this side squared has to equal this side squared, that would then result in this third side being equal to the square root of a squared minus u squared. And that's where you see this triangle sitting right here is what I just drew. So this triangle is the geometric representation of this substitution. Now, where does the cosine piece come into play? Well, the cosine piece comes into play by looking at that triangle and saying, okay, now let me take the cosine of theta. Here's theta. If I were to take the cosine of theta, I need to do the adjacent side over the hypotenuse, which is the square root of a squared minus u squared over a. And then if I move a to the other side of the equation by multiplying, what do I have? I have a cosine theta equals the square root of a squared minus u squared. So that's how you see that equality working out. The triangle came from this substitution. Then in working with the triangle, we get this substitution. So two different ways of seeing it. This is more sort of the computational way of doing it. This is the geometric way. But either way, it doesn't really matter how you realize this works, but that this substitution works. Now let's put it to use. Here's an example. Look at the square root in the denominator. That is in the form of the square root of a squared minus u squared, where a is 3 and u is x. So if we use the substitution where we're going to let u equal a sine theta, and therefore the square root of a squared minus u squared is going to end up equaling a cosine theta, then in this particular problem, that tells me that x, which is u, has to equal 3 sine theta. If we make that substitution, then the square root of 9 minus x squared will end up equaling 3 cosine theta. Okay, so this is the general substitution. This is how it relates to this specific problem. Now, it's a substitution problem, right? So this whole root here is going to come out and be replaced with this. This x here can come out and be replaced with this. The only other extra piece we need to pull out of this integral is the dx, which comes from the same place it always came from by taking the derivative of x. The derivative of x would be 3 cosine theta d theta. And so now we have a way of substituting all these x pieces out and replacing them with all of these theta components. So now look at what happens. Dx is 3 cosine theta d theta. X is 3 sine theta, so x squared would be 9 sine squared theta. And the square root is equal to 3 cosine theta. And now it's time to do this integral instead. Well, this 3 and this 3 would cancel. This cosine and this cosine would cancel. And so ultimately I would get the 1/9, I could pull the 9 out, times the integral of d theta over sine squared theta. Remember, in order to integrate something like this, you need to go, oh, well, how do I do it? Well, I'm going to rewrite this, and I'm going to say this is 1/9 times the integral of cosecant squared theta instead, because 1 over sine is cosecant. So 1 over sine squared is cosecant squared, and the only reason I'm going to write it that way is because this should be an easy integral for you. You should have your basic integrals memorized. And if you do, you should know right away what the answer for this integral is. So we all know that the answer is negative cotangent, so this would be negative 1/9 cotangent theta plus c. Problem is that's not it. We're not done. I mean, that's the answer for now. But think about it. We did a substitution. Whenever you do a substitution, you need to go back to the original variable, right? This was an integral in terms of x. We got an answer in terms of theta. So what are we going to do? We need to resubstitute. How? Well, there's two ways to do it. One, cotangent is cosine over sine. And we know that cosine of theta would equal the square root over 3, and sine of theta would equal x over 3. So if I take this divided by this, that's the cosine over the sine. Well, the 3's would cancel, so I'd end up with negative 1/9 square root of 9 minus x squared over x plus c. And there's your answer. There's another way we can do this. Remember, there was that triangle. Here's theta. It's a right triangle. Here was u was here, which in this case u was 3 sine theta. Right, that was your u, which in our case, u was x. And this was supposed to be your a, which was 3. And so then this would be the square root of 9 minus x squared. And if we were to take the cotangent of theta, cotangent needs the adjacent side over the opposite side. So if I take this divided by this, I get the same answer I got here. So either way, it doesn't matter. Some people like doing it the geometric way. Some people like to just use the substitution. But either way, you got to get back to x. Now, one more thing before I move on. Looking back at this integral, why did I even do this? Why did I even try trig substitution? Well, that square root was kind of an indicator, 1. 2, it's not really anything else that's going to work. This on its own doesn't really fit anything nicely. If this x squared wasn't here, that looks a lot like an arc sine, but the x squared is there. There's no substitution that's going to work unless I had an extra x up here. So nothing else would really work. The square root's kind of the indicator that I have something that I can use in this trigonometric substitution. So something you're going to have to get better at. Here's another one. In this case, it's for the square root of a squared plus u squared. So a different root. And again, the root isn't really the big part. It's the thing inside. And I'm going to explain that at the end of the lesson, why the square root doesn't really matter. Most of the ones you're going to see right now are going to have the square root, so we're going to use that, but I'll show you why the square root's not really even that significant to this. It's the thing inside the square root. So anyway, this says if we were to let u equal a tan theta, the square root of a squared plus u squared can turn into a secant theta. Why? Well, for the same reason. If I was to look at this square root, a squared plus u squared, again, a is a constant, u is a function of x. So think, I don't know, the example would be the square root of 25 plus 4x squared, something like that. A would be 5, u would be 4x. So anyway, if I were to look at this, and I was to let u now, instead of equaling a sine, let u equal a tan. Because if I let u equal a sine theta in this square root, it doesn't do anything. It just makes it look even worse than it already does. But if I use this particular substitution for u, look at what happens. I get a squared plus a tan theta squared, which if I square both of these, I get the square root of a squared plus a squared tan squared theta. I factor out the a squareds. I get 1 plus tan squared theta. That's messy. Let me clean that up. 1 plus tan squared theta. But 1 plus tan squared is equal to secant squared. So I get a squared secant squared theta. Square root both of those because they're multiplied together I can, and I get a secant theta. So you see, if I use this substitution, the square root becomes a secant theta. I could do it the same way I did the other one. And another way to do it is to say, well, u over a equals tan theta. That's just dividing this a to the other side. Looking at a right triangle, this should be the opposite side. This should be the adjacent side. So if I'm finding the tan of theta, opposite over adjacent, u over a squared plus u squared has to equal this side squared, Pythagorean Theorem, making this the square root of a squared plus u squared. Then if I was to take the secant of theta, I would need to take the hypotenuse over the adjacent. And, well, sorry, not squared. And then multiply that to the other side, and you see the square root equals a secant theta. So this triangle comes from this substitution, and this substitution all revolves around that particular root. So something you're going to have to remember, which root yields what substitution, and this is a different one. So let's see an example. So here's one where you look at the square root. In this case, this is the square root of u squared plus a squared. It doesn't really matter if it's u squared plus a squared or a squared plus u squared, because they're added, the order doesn't matter at all. The subtraction, the order is really important. But in addition, order doesn't matter. So if we looked at this one, u would be 2x, because that would again give me u squared here, and a would be 1. The substitution we're going to use is that u has to equal a tan theta, so that the square root of a squared plus u squared can equal a secant theta. Okay? Secant theta. So as it relates to this problem, that tells me that 2x is going to have to equal 1 tan theta. so that the square root of 4x squared plus 1 can equal 1 secant theta. Now we need the dx. Well, this is 2x, so dx would just be 1/2 of the derivative of this, just dividing the 2 over. And derivative of tan is secant squared, theta d theta. And so you make your substitution that dx is going to come out, secant squared is going to go in its place, the square root is going to come out, the secant is going to go in its place, and you're looking at the integral of 1/2 secant squared theta d theta over secant theta. Now it's a matter of doing that integral. So we can simplify, cancel this with one of these secants. The 1/2 comes out. We have the integral of secant theta d theta, and that's it. Well, that's an easy integral again. You should know this basic integral. So we get 1/2 natural log secant theta plus tan theta plus c. Well, that's all well and good, but now remember, resubstitute. Well, what do we see up here? Secant theta equals this, tan theta equals this. So put them in. 1/2 log of square root of 4x squared plus 1 plus 2x plus c. Pretty simple. Again, why did we do this? Because we don't have any other options. One, there's no other way to get this done. It doesn't look like anything else that we can do. Substitution won't work. None of our basic trigonometric functions will work. None of our other basic functions will work. If the square root wasn't there, if it was just 4x squared plus 1, that's an arctangent integral. But the square root is there, and so now it's no longer an arctangent integral. And so the square root is kind of the indicator of the substitution we're going to use. Here's another one. This is another substitution of the same, because you got to remember that the 3/2 power is the square root of x squared plus 1 cubed, right? Third power, second root. So it's really the square root of x squared plus 1. And when you do this, remember, it doesn't matter whether or not that power is inside the root or whether that power is outside the root. So what do we have? We have another square root of u squared plus a squared. So what are we going to do? We're going to say u has to equal x. A would be 1. The substitution that goes along with this is to let u equal a tan theta, so that the square root of u squared plus a squared can equal a secant theta. Okay? And I always think it's good to write this down so you remember it. The more you write it down, the more you'll commit it to memory. But as it relates to this problem, u, which is x, is going to have to equal 1 tan theta, so that the square root of x squared plus 1 can equal 1 secant theta. And then we need a dx, which will just be secant squared theta again, d theta. So same substitution, so it all looks fairly similar at this point. Here's where it's a little different because this is a different integral. So we're going to plug everything in. Dx is secant squared theta d theta. The square root of x squared plus 1 is secant theta, but that's being cubed. So this is secant theta cubed. We simplify. We get d theta over secant theta. Well, that's a pretty easy one because 1 over secant is actually equal to cosine. And the integral of cosine is really easy. That's equal to the sine of theta. And we just have to resubstitute. But the integration was really easy. That's why we do the substitution. You always do substitution to make your integration easier. It doesn't seem like that's going to happen here. There's a lot going on with all this. But when it all is said and done, the integral that we had to do was just the integral of cosine theta d theta. And it doesn't get much easier than that. So now we got to resubstitute. We could look back to our substitution that we did and try and use that to get back to x. In this case, it's not going to be that easy. I have a tan theta, I got a secant theta, but here I have a sine theta. So instead what I'm going to do is I'm going to draw my triangle. Remember, you have two options here. You can do the geometric way of resubstituting, or you can do the more computational way of resubstituting. I like the geometric way. So it all comes from here. That says that x equals tan theta, right? You can write this as x over 1. Well, the tan of this theta is going to be created by using the opposite side over the adjacent side. Well, if this is the answer I'm going to get, the opposite side has to be x, and the adjacent side has to be 1, making this the square root of x squared plus 1. And now, if I'm going to take the sine of theta, I need the opposite over the hypotenuse. So the sine of theta should equal x over the square root of x squared plus 1 plus c. Now I'm back to x. Don't bother rationalizing that denominator. This answer is perfectly fine, and we're good to go. So you see why this is a really great way of integrating. It just seems to work out so perfectly. Well, that's because it does work. That's the thing here, though. When trig substitution is supposed to be used, it works wonderfully. You see it just making itself work out. When trig substitution is not supposed to be used, but you use it anyway, this whole thing becomes a mess. And you kind of know right away that, yeah, maybe I went down the wrong path here. I should probably try something else. And now the final substitution. The final substitution for square root of u squared minus a squared. And this one's different than the first one because of the order in the subtraction. Here the u, which is the function of x, comes before the constant. So this one, we're going to say that u equals a secant theta, and what that does is it turns that square root into a tan theta. Now notice we have a plus or minus here. I'll explain that in a second. But the reason for the substitution coming about is, again, because of basic, arithmetic with our identities. And so if we took the square root of u squared minus a squared, and we let u equal a secant theta, if we let it equal a tan theta or a sine theta, it doesn't do anything for the square root. What it does, it just makes a big mess. But if we let u equal a secant theta, what happens is that the square root becomes a squared secant squared theta minus a squared. Factor out an a squared. Secant squared theta minus 1. Pythagorean identity for this says that that's equal to tan squared. Square root both of those, and you get your a tan theta. Now, as far as the plus and minus goes, what it says is that if u is greater than a, we use the plus. If u is less than negative a, we use the minus. Now, we can only determine whether or not u is bigger or smaller than a or negative a if we know what u is. And u is a function of x. Well, the only way we'll know with that is if we know what x values we're talking about. Well, we only know what x values we're dealing with if we have an interval of x, which would only come into play in definite integrals. So as far as indefinite integrals go, you just keep the plus and minus there. If we have an definite integral, then we'll know whether or not u is greater than a or u is less than negative a, and whether or not to use the plus or minus. And the reason for the plus and minus has to do with some of the trigonometry in terms of the values of the tangent as they relate to the values of the secant for certain angles as you move around the unit circle. Here's the triangle that goes with the whole substitution. You could write this as u over a equals secant theta. So secant is going to be your hypotenuse over your adjacent. So there's your u over your a, making the third side square root of u squared minus a squared, so that the Pythagorean theorem works, that this side squared plus this side squared equals this side squared. And so you can see where then the tangent theta equaling the square root is going to come into play. So here's an example. In this case, looking at the square root that we're dealing with, we have a square root in the form of the square root of, well, let me use a different color you can see, the square root of u squared minus a squared, where u equals x and a equals root 3. With that tells me that my substitution should be that u equals a secant theta, so that the square root of u squared minus a squared can equal a tangent theta. Now there was a plus and minus here. In this case, we can determine if we want the plus or minus because we know what x's we're talking about here. If u equals x, then what this is telling me is that u is going to be between square root of 3 and 2. And if a is the square root of 3, can we determine whether or not u is greater than a or u is less than negative a? Well, in this case, yeah. If these are the u's I'm talking about, and this is the a we're talking about, then yeah, this happens. So if this is the case, then we're going to use solely the plus. So let's make the substitution for this particular integral. Well, we said that u, which is x, is going to have to equal a, which is square root of 3, secant theta. And that will then in turn make the square root of x squared minus 3 equal a, which is square root of 3, tan theta. And then we just need to figure out what dx equals, which in this case would be the square root of 3 secant theta tan theta d theta, because that's the derivative of secant. Make all your substitutions in here, and we're good to go. Well, we're going to get the square integral of the square root, which is square root of 3 tan theta, over x, which is square root of 3 secant theta, times dx, which is square root of 3 secant theta tan theta d theta. There's going to be a lot of simplifying that we can do. Cancel, 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 cancel. But don't forget, this is a definite integral. And these are x values. Well, we just switched the variable over to theta. So you have two options here. Remember back to substitution. There are two ways to do definite integrals with substitution. One option is I'll just keep integrating as I go, and then eventually I'll get back to an x answer. Once I get back to an x answer, then I can evaluate between the square root of 3 and 2. The other option, though, is to turn these x values into theta values, in which case I don't have to go back to x. I can leave my answer in terms of theta, and then I would have theta values to plug in. It doesn't matter which way you do it. Most people don't like doing it that second way because they're just not used to it. I think most people just go back to the original variable, but it's just something to think about. Let's continue down the road of this integral before we think about doing that. So remember, we're going to be integrating, what do we have here? Square root of 3 tan squared theta d theta. Now, in order to do that, how am I going to do this? Well, think about it. This is where some of those trigonometric integrals we covered in the last lesson will come in. I have tan to an even power. One thing we said to do is to use secant squared here. So I'm going to rewrite this integral as the integral of the square root of 3 times secant squared theta minus 1, which will then in turn give me square root of 3 times the integral of secant squared is tangent of theta, and the integral of 1 with respect to theta is theta. Okay? Now, we have a decision to make. We got this interval where x equals the square root of 3 and x equals 2. And I got to decide, do I want to turn these back into x's so that I can plug these in, or do I want to switch these over to thetas? Well, the substitution for the first piece is not hard. Tan theta has to equal the square root of x squared minus 3 divided by the square root of 3. Now this one, however, is a little bit trickier. It's just the theta. It's not a tan theta. It's not a secant theta. It's just the theta itself. So I got to figure out what's theta equal. Well, if I look at this one right here, I could use this as well. Either substitution will work. If I look at this one, which is typically simpler, I could see that x over the square root of 3 equals secant theta. And then what I can do is get rid of the secant by doing the inverse secant, and I would have the arc secant of x over 3, square root of 3, equals theta. And that can go there. Now looking at all that, I have x's in both cases, and I plug this in. That could be a little bit complicated, but you could do it. But let's look at what would happen now if we didn't do that. Let's look at what would happen if all we wanted to do was change these to thetas. How would we do it? Again, we have a substitution that tells us how x and theta are related to each other. So if x equaled 2, and x has to equal the square root of 3 secant theta, then I just take this equation and solve for theta. And if x equals the square root of 3, and x has to equal square root of 3 secant theta, then I could solve that equation for theta. So in this case, divide this by square root of 3. And now I have secant theta equals 2 over the square root of 3, knowing that secant is the reciprocal of cosine, and this is the reciprocal of square root of 3 over 2. That tells me that theta would have to be 1/2. Sorry, not 1/2. Theta would have to be pi sixth. And if I looked at this to be divided by square root of 3 here and here, and canceling, this tells me that secant theta equals 1. And I have to think about what angle would secant of theta equal 1, and thinking about reciprocal of cosine, theta would have to be 0, because the cosine of 0 equals 1. So what I could do is say that instead of evaluating between square root of 3 and 2 for x, I could say I could evaluate between 0 and pi sixth for theta. Well, now that these are theta values, they can go right in here. Well, it's probably easier to plug those into here than to plug those into what we had before. So I'm going to try and get this cleaned up here. And now we get the square root of 3 times tan of pi sixth minus pi sixth minus tan of 0 plus 0. Well, tan of 0 is 0. 0 obviously is 0. So I get this. Tan of pi sixth is square root of 3 over 3. So I end up with square root of 3 times square root of 3 over 3 minus pi sixth. And there's my final answer. A lot going on in this problem with the substitutions, but we were able to get it to work out. So then what you're going to see is that there are formulas for integrating a lot of different standard integrals. And I talked about it when we did the trigonometric integrals. And the same thing goes for these square roots that we've been talking about through trig substitution. So if all you're doing is integrating the square root of, say, in this case, a squared minus u squared, or u squared minus a squared, or u squared plus a squared, and that's the only thing in the integral, there's a formula for the answer. Now, in order to use it, it would require you to know it. And I don't think most people would sit here and memorize these formulas. And yeah, while you could look them up in, the future to use them, I think the most likely way you would do an integral like, say, this one right here, would be simply doing it using the way we've done all the previous examples and doing your standard trig substitution, which is where these formulas come from. They come from doing it by applying the substitution. So that's how we'll do this example. So in this case, we're looking at a square root of a squared minus u squared, where a is 2 and u is x. So the substitution that goes along with this is that u equals a sine theta, so that the square root of a squared minus u squared can equal a cosine theta. So for this problem, u is x, and a is 2, so x will equal 2 sine theta. That way the square root of 4 minus x squared can equal 2 cosine theta. And then dx would equal 2 cosine theta d theta. So we make our substitution here. We end up with 2 cosine theta times dx, which is another 2 cosine theta d theta. And so we end up with the integral of 4 cosine squared theta d theta. And then we have to go from there. Well, this is cosine to an even power, so we're going to have to use our power reducing identity. So that'll be 1 plus cosine 2 theta over 2 d theta, in which case I'm going to split this apart. I'll also distribute the 4 into both of them, just to make it easier. So what do I have? I'm going to have a half times 4, which would be 2, plus 4 times a half cosine 2 theta, which would be 2 cosine 2 theta d theta. So we integrate with respect to theta, and we'll get 2 theta, and then this becomes sine 2 theta. It should be sine 2 theta over 2, but with this 2 out here, they cancel, and we get this, plus c. And all we have to do now is to go back to x. Now, this one's a little trickier. One, because we have a theta sitting here by itself, which we've talked about before. And the other one is because of this one. This is sine 2 theta. We know what sine of theta could equal. Just divide by the 2, and you say sine theta equals x over 2. But sine of 2 theta is different. And so what we're going to do here is we're going to use the double angle identity to help us out. As far as this theta goes here, I'm going to use this equation. I'm going to say that x equals 2 sine theta is the same thing as saying x over 2 equals sine theta. Is the same thing as saying the arc sine of x over 2 equals theta. And so I divided by the 2, then I took the inverse sine to get rid of it, so I get theta by itself, therefore the arc sine. As far as the sine 2 theta here, it's a double angle identity. So first let me take care of this. This will be 2 arc sine of x over 2. And then this sine 2 theta, the double angle identity says should be equal to 2 times the sine of theta times the cosine of theta plus c. Well, now we just have the sine of theta and the cosine of theta, and we can use this substitution that we have to do that. So we end up with 2 arc sine of x over 2 plus 2 times sine would be x over 2. And cosine would be the square root of 4 minus x squared over 2 plus c. We can cancel this 2 and this 2, and other than that, we have our answer. And if you compare it to what you see here, it's going to give you the same answer. And so this is the more likely way you would do a problem like this. I don't think that these formulas are very convenient in practical terms. Now, I talked about how the square root is not really the most important part of the determining the substitution. It's what's inside the square root. So when we say we have the square root of a squared minus u squared, and that automatically dictates that u should equal a sine theta, so that the square root of a squared minus u squared could equal a cosine theta. The square root itself is not really the important part here. It's what's inside the square root that matters the most. That order of that subtraction is really what dictates this substitution. Because what I can do is I can look at this equation here, and I can move that square root around. I can write this as a squared minus u squared equals a squared cosine squared theta. And all I did was take the square root of both sides of this equation here to get this. And so this would still be the initial substitution. If u equaled a sine theta, then we could say that a squared minus u squared equals a squared cosine squared. And so while it's pretty easy to identify the square roots, they're not necessarily the requirement for using trig substitution. The inside of the root is the primary requirement. So let's just hypothetically say I gave you this integral of dx over 4 minus x squared. And I said, let's do this integral. Well, one way to do it, there are others, one of which we're going to learn in the next lesson, called partial fraction decomposition, which would probably be the more likely way you would go about this one, but you could do trig substitution. I could use this exact substitution we have here. If u is x and a is 2, then I have a squared minus u squared. And therefore, x should equal 2 sine theta, and 4 minus x squared should equal 4 cosine squared theta. Again, a squared cosine squared theta. Dx would equal 2 cosine theta d theta. And then I would say that I get 2 cosine theta d theta over 4 cosine squared theta. Well, the cosines would cancel, the 2 and the 4 would cancel, and I would get 1/2 the integral of d theta over cosine theta, which would then give me 1/2 times the integral of secant theta d theta, and I would then get 1/2 times the log of secant theta plus tan theta plus c. Switch back to x's and you're done. Well, I have secant and tan. My substitution was all sine and cosine. So in order to go back, I'm going to use my triangle. Right? Sine is going to be equal to x over 2. So that's opposite over hypotenuse, putting the square root of 4 minus x squared here. So that a squared plus b squared equals c squared. And then I'll take the secant and tangent of theta here, and that'll get me my answer. So 1/2 log of secant. Secant is hypotenuse over adjacent, so that would be 2 over the square root of 4 minus x squared, plus tangent would be opposite over adjacent, so x over the square root of 4 minus x squared plus c. But the whole point of me giving you this example, there's the answer, but the whole point of me giving you this example is that the integral didn't have the square root in it. And it didn't need to have the square root in it for us to still be able to use trig substitution. It's this piece here that's the most important part. Now again, most of the ones you'll see right now in this section are going to have the square root. So they're going to be a great indicator of, I know I should use trig substitution, and then I need to know which trig substitution I should use. However, in most cases, that's going to happen. Just remember, it's not necessarily a requirement. You could still do trig substitution even if that square root isn't there. If you had just a squared minus u squared, a squared plus u squared, or u squared minus a squared was the only piece you had, you can try to use trig substitution still. And it's just about turning this piece around by squaring both sides of the equation and getting rid of the square root.